Yeah, thank you for the kind introduction. And here you can see what I would like to briefly talk about today. And as you just introduced who I am and what I do in NFTI for Chem in the task area 6, I think I can safely skip most of it, but maybe just say a few words about NFTI for Chem and my role in it. So working in task area 6, I'm tasked with developing ontologies, curating ontologies, existing chemical ontologies mostly, and help in advising various aspects about their use. And as part of that, I'm also part in the NFTI section metadata consortium working group called Ontology Harmonization and Mapping, where we try to do exactly that, harmonize the use of ontologies and the mapping between ontologies throughout the whole NFTI consortia. And currently I'm working also with other people from the NFTI for Chem consortium and external institutions on the vibrational spectroscopy ontology, and did some stuff for NMR spectroscopy. So what ontologies are in a nutshell, they are a formally specified conceptualization that is focused on answering the question of what can be represented in a specific domain. So for the chemists, this might be not so unfamiliar, because what chemists usually do when they talk about what they're doing, like they codify their knowledge about molecules and reactions and the underlying chemical mechanism using common symbols like the reaction arrows or structural formulas and systematic names. And ontologies that we are using, those formally specified conceptualizations, they're usually specified in formal text that uses the resource description framework RDF and the web ontology language OWL. And here I want to give you a very brief example of ontologies that are prominently used: the basic formal ontology and the relation ontology, and how they are used together with a time ontology to give you a very brief pattern of how processes work. So we have a process, a very abstract class for the basic formal ontology, and we have the other very abstract class called continuant, which is basically a thing that keeps its identity throughout time. And such continuants participate in processes, and such things, both processes and continuants, can have attributes which basically are characteristics that specifically depend on those things. And if those things stop to exist, then since the attributes are specifically dependent on those, they also cease to exist. And more concretely, we have ontologies mainly from the ontology of biomedical interest, which reuses quite a few of other ontologies. What you can see here is a pattern of classes, which are the things defined in ontologies that represent real world entities, whether material or immaterial. And what you can see here is the pattern for an investigation and an assay, and how an assay is part of an investigation. And this is for us important because we would love, or we like to use this pattern in order to annotate research data to make it more findable and interoperable. So I don't think I should go much into detail of what you can see here, but basically the arrows between the classes, which are like OBI planning and OBI assay, those are the classes, and the arrows represent the relations. So what you can see is that an investigation has always as part a study design execution, which has as part usually an assay, which executes a certain specification. Basically, the plan that you either written down or copied from elsewhere that tells you how to do your assay, how to set your devices, how to configure them, how to prepare a sample, and how to measure in what kind of timeline or using what kind of other devices and other parts. And of course, such an assay is always about some material entity, your chemical substance you want to analyze and find out what's the structure of it, for instance, and therefore this chemical entity usually has an evaluant role, and the devices used in assays have certain functions. That's why they are used in such assays. So yeah, this is the general investigation in assay pattern. And what I was asked to talk about briefly is what ontologies there are for chemistry specifically. And in order to talk about this, we also need to be aware that, as you've already seen with this abstract process pattern from BFO, there are ontologies that are very abstract and they are called upper ontologies. And then there are ontologies that are a little less abstract, which we usually call mid-level ontologies. And of those mid-level ontologies, some cover general domains like information, such as the information artifact ontology, or general domains of science. Of course, although you have the ontology for biomedical investigations here, the name sounds very specific to biology, but actually, since this ontology is very big and old, has been out there for quite a while, we find very common scientific terms like investigation, assay, and certain devices like microscope, for instance, and beaker, and such things we already find in that. So we should be aware that we do not have to define such things anew, but rather look at existing ontologies, although they might be named not as general as one would assume. Similar is the case with the phenotype and trait ontology, coming also from the biomedical realm. This ontology has very basic attributes of things like physical process attributes such as duration or concentration for material entities, or temperature for material entities, and so forth. And then we have ontologies for units, standardized units that we need to use in order to describe our data, but also ontologies that are not adhering to certain upper level ontologies, as do IO, OBI, and PATO, for instance. EDAM is rather an ontology without any upper ontology that can also be used in certain kind of contexts. But for chemistry specifically, we have the ontologies that you can see here and that are described in more detail on paper we published. And basically, what I'd like to tell you with showing you this graphic is that there are already good, or rather quite well, ontologies existing that cover already a very broad range of discourse that we would like to use when describing research data. And yeah, you can see the range goes from material entities. So we have KBI, for instance, that is about molecules and atoms and particles. We have CHMO, which is the chemical methods ontology, which is for material entities in terms of lab devices. Yeah, the same goes for PROCO, the process ontology. Then we have very natural processes in the molecular process ontology called MOP is for such chemical process, such the general process such as reduction, oxidation, and another ontology, RxNO, is used for named reactions like the Diels-Alder reaction. So basically, we already have quite a few things present that we can directly reuse for annotation. You can check them out in the NFTI for Chem collection that is available in our terminology service. But since they have been developed over time from different groups and documentation on certain patterns that should be reused, design patterns that are coming from upper or mid-level ontologies, since this documentation is spread out over multiple publications, but also hidden quite often in discussions happening on GitHub and in mailing lists. The development is not always in sync with each other. So there is still work to do in terms of harmonizing certain ontologies like classes and the chemical methods ontology that are also present in the OBI ontology. And if we want to use both together, it would be better to say there should be only one of such class, there should be only one microscope defined and only one ontology, and let's agree to use that one instead of the other one and rather obsolete the other one. So such are works that have to be discussed in working groups that deal with harmonization or mapping. And when we do this, we also want to make sure that we're not developing ontologies only, but to use ontologies in concrete use cases. And more concrete use cases would be to have metadata schemas that define the layout of applications like repositories or electronic lab notebooks. And if we map ontology terms into those data schemas, we can make sure that it's definitely easier to import and export the data coming from those applications in a format that will allow to communicate between applications more easily, because you then have sort of a synchronized data format. You do not have to have the same data schema, but if this data schema is mapped to the same ontology terms, then it's definitely easier to understand that a key in one schema represents the same key in another schema, although it is nested in a different structure, for instance. And also for this, literature sources like the IUPAC Guidebook can help a lot in this harmonization and standardization approaches that we still have to do, because they provide single points of truth when it comes to the definitions that we should adhere to according to, domain experts working in the Guidebook editorial board, for instance. And now coming to more concrete use cases, like why do we need and want ontologies, apart from the fact that it's easier to make applications interoperable by having their data schemas mapped to ontologies. In a more broader sense, it would help us to semantify research data from the very beginning. So when I have an electronic lab notebook and I type my research data that I measure in the lab into it right away, and as I said, the data schema is mapped to ontology terms, I do not have to worry that much about of making my data fair, because when I then click on export and have my data set exported in some kind of format, it should be very easy to also produce a format that can be ingested in other databases and therefore be reused rather quickly and does not have to be processed in complex ETL pipelines. And this, of course, improves apps and services like electronic lab notebooks, but it would also be used to enhance standard specifications. And here's an example. As I said earlier, I've did some experiments together with Oliver and getting input from Johannes as well about NMR spectroscopy, and we were looking at what ontologies exist and have existing NMR spectroscopy relevant terms, so classes and relations we can use in order to do such things as semantify research data. So what we did is building a prototype where we had a data schema which we mapped to ontology terms, and this data schema was written in a linked ML framework that allows you to write a data schema in YAML, very user-friendly, and map those YAML schema elements to ontology terms, and then auto-generate Python classes from it, which can be used to then use another Python library to ingest JChem-DX data, in which we have NMR data stored actually, and then use this schema and the Python classes that were generated to convert JChem-DX into another format, into a TTL, which you can see down here. And this TTL is basically a small knowledge graph that has your JChem-DX data semantified, and you know, okay, this is my sample, this is the nuclei that was observed, And this is the dimension of the resulting spectra, for instance. And when you have this, you can then put it up in a graph database, which you can then connect with other graph databases such as Wikidata or a MassBank or PubChem, which has an RDF endpoint, and then you can do federated queries over it, and thus very easily connect multiple databases with one query to each other, and answer questions that you could not answer by querying only one of these databases, but at the same time answer those questions in a way that it's much, much easier than traditionally asking them via standard APIs, because for doing that, you would have to know the API schema of each database, and this is usually quite different. But if you do it this way, you have one common language that you can use. And Sonia also asked me to say something about how ontologies could be used in machine learning context. I'm not an expert on this. I'm interested in it, I must say beforehand, and I'm trying to follow what the people from the biomedical sphere are experimenting with ChatGPT at the moment and how they do it. But like basically one could say, if we have a text like this, which could be a standard experimental description from a paper, and we want to know what this means, and tell this to a computer and be able to use this to understand new experimental section text, we would need to have training data that marks up such text. So what we want basically is to have entities recognized that are in those texts, entities such as what are the specified reactants, what are we talking about, a Diels-Alder reaction, a certain kind of reaction, or the molecules that are involved, and the circumstances that are there, that are present for this reaction to be happening and such. And so when we have such marked up text, we can use this marked up text, for instance, as training data to find such markups and semantify other text without having to read it and annotate it manually. So we can build knowledge graphs from this, but at the same time, we can then probably also analyze existing knowledge graphs and find errors in this, and yeah, improve the way we do queries. When we do things like this, it's much easier, for instance, and you see this query here. In order to ask a question like this, you would have to know Sparkle. You would have to write this Sparkle code. And what ChatGPT could be doing, or similar large language models, if they are trained well with good labeled data, is you could ask this question as a plain text question, like show me the corresponding mass bank ID of mass spectra on a given compound of this NMR sample, and then it could generate you the query, or even execute the query for you, because it knows what it needs to look for, because it had good labeled training data. Yes, now's the time for asking me anything.